So hi everyone, for this video we're going to discuss additional problems with relating to um, normal stress, shear stress, and deformation. Okay, we have here number one, a steel bar of cross section 500 mm squared, so that would be the cross section of this steel bar, is acted upon by forces shown. So determine the total elongation of the bar. For steel, we use modulus of elasticity, which is 200 gigapascal. So the first thing that we need to do is to determine what would be our working equation. Now, we know that for deformation, delta is equivalent to PL over AE. Okay, PL over AE. So we know the length. We have 0.6 meter, 1 meter, and 1.25 meter. Now what we need to determine would be the internal. Okay? What would be the internal forces in each of these segments? That would be PL1, PL2, and PL number 3. So for solving for the P's, I'll be using a shortcut method by drawing the actual diagram. Okay? So I'll just be aligning it with my load diagram. So this is how my actual diagram would look like. So actual diagram. Okay. So if it is in tension, it would be positive. If it is compression, then it would be negative. So the 50 kilonewton here is in tension. So that would be a 50 kilonewton above the reference point, which is 0. So that would be 50 kilonewtons. Okay. So 50 kilonewton up to point B. So that is a straight line. Then from there, I have a 15 kilonewton, which is opposite of 50 kilonewton. Therefore, the direction of 50 kilonewton. Therefore, it is compression. So 50 minus 15, that would go down to 35. Okay, so that is now 35 kilonewton. Then from point B to point C, it would be a straight line. Then at point C, I have here a 10 kilonewton on the direction same as the 50 kilonewton. Therefore, this is in tension. So it would go up to 45. Okay, so that would be 45 kilonewton. Then from point C to point D, that would be again a straight line. And again, at point D, I have a 45 kilonewton, which is in the direction of compression. Therefore, it will go back to 0. Okay? I started with 0, I ended up with 0. Okay? Therefore, P1 is equivalent to 50 kilonewton. P2 is equivalent to 35 kilonewton. Then P3 is equivalent to 45. So that is 45 kilonewton. Okay, then I can now solve for my deformation. So for the elongation, that would be delta is equivalent to delta 1 plus delta 2 plus delta 3. And that is equivalent to 1 over EA. Take note, or AE, that the area of the rod from point A to point B is constant at 500 mm squared. Likewise with the modulus of elasticity, which is 200 gigapascal. So we can factor out AE. So we have here, we have P1 L1 plus P2 L2 plus P3 L3. Okay, so substituting the values, we will be having 1 over the area, which is 500 mm squared. So 500 mm squared. Now 200 gigapascal, we can convert that to 200 megapascals, and MPa is Newton per mm squared. So that is 200,000. So that would be MPa. Take note that megapascal is also equivalent to Newton per mm squared. Okay, so this is times, that is Newton per mm squared times what would be the P1. P1 is, what is P1? P1, ay, 50. So that is 50,000 newtons. So 50,000 newtons times L1. What is L1? L1 is 600 mm times 600 mm plus what is P2? We have 3,500 newtons times what is the length? We have 1,000 mm plus we have here 4,500 newtons times the length of 1,250 mm. So substitute that in your calculator. We will be having the value of 1 over 500 times 200,000 times 50,000. Yeah. No. This is 35,000. Then this is 45,000. Plus 45,000 newtons times 1,250 mm. Okay, so 50 times 600 plus 35 times 1,000 plus 45 times 1,250. And that is equivalent to 1.2125. Now, what would be the unit? Okay, so mm squared for the denominator. For the numerator, it is just mm. So, no, this will simply cancel out. Mm squared, the Newton will cancel out. Therefore, the unit is mm. So, the total elongation of the steel bar is 1.215 mm. Okay, so we have here number 2. The 3-bar assembly shown in the figure supports a vertical load of P. So this is the vertical load of P. And we have here the 3 assembly of the steel bar. So bar AB and bar BD, so AB and BD are identical, each of length L. So you have here a length of L, and they have the same cross-sectional area of A1. The vertical bar BC is also of length L but of area A2. So L1, 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 but you have A1, A1, A2. All bars have the same modulus of elasticity and are pinned at ABC, A, B, C, and D. Determine the actual force in each of the bars. So how are we going to do that? First, we will be using the equations of equilibrium. So if we are to draw the free body diagram, so from the free body diagram of joint B, so from joint B, we will be having 4 components. Okay. So we have here CB. So you have here BC. You also have here point P. And you also have here AB. Okay. So you have here PAB and PBD. But according to the problem, AB and BD are identical. So let's say this is P1. This is also P1. Okay? And let's say that the load at CB would be P2. Okay? And the angle here with respect to the horizontal is theta. Likewise with this, the angle here is theta. Okay? Now, from the equation of equilibrium, we can have one equation, which is the vertical. Okay? So, summation of forces, vertical is equivalent to 0. All forces that are pointing upward should be positive. So, what are those forces? So, we have P2 minus P1. No. No. This is plus. Plus P1 sine theta. Okay? But there are 2P1. So include here a constant of 2 minus P is equivalent to 0. So this would be my first equation. Okay? Now the additional equation would be coming from this with the condition of the setup. So if this is your imagine if this is your figure, you do not have yet the P, it is in a state of equilibrium. So we do not have any internal forces because CB will not be having internal load, likewise with AB and BD. But if we apply P, then mag-iiba na yung condition natin. So if we are going to apply P here, imagine segment CB. So if I am to redraw segment CB here, so ito siya. This is point C, this is point B. It would elongate somehow. Okay? From this point, pupunta siya to this point, and let's say that is B prime. Somehow it would elongate because there is a load being applied. So let's say that that is delta 1. For segment AB, there would also be a change. Okay? Imagine this one, segment BC elongated. Okay? Segment BC elongated. Therefore, segment AB will somehow compress. Okay? There will be a compression at segment AB. So from an original of point, let's say this is point B, from an original point of B, since point B here elongated, this one, AB, will have a shortening. Okay? So let's say this is B double prime. Okay? So therefore, there is also a deformation at this point. So let's say that is delta. Okay? With that, there was a rotation that occurred. Okay? Kasi from this point, bumaba at a certain point. So from this position, there was a rotation at point A. Okay? Nagkaroon tayo ng rotation at point A. So from an original position of point B, it so happened na nandito na siya sa point, let's say this is B triple prime. Okay? So with that, we can create a right triangle. Okay? So the angle here is theta. Therefore, the angle also here is theta. Okay? So from an original position of at B, it went down to B prime. If we are to magnify this, it would look like this. Okay? So yeah. We have here theta, and we have here the deformation. Deformation delta. Okay, so what we are interested here is the deformation on this side. So B to B triple prime. So let's say this is delta triple prime. Okay, so why are we interested in delta triple prime is because we can relate it with respect to CB. Okay, so in solving for delta triple prime, it is a sine function. So sine theta is equivalent to delta over delta triple prime. Therefore, the deformation is equivalent to delta triple prime sine theta. Okay? So, we know that our working equation is delta is equivalent to PL over AE. Okay? So, delta here, so delta is equivalent to P1 L over area 1 times 3 times E. So substituting delta, we will be having delta triple prime sine theta is equivalent to P1 L over A1 times E. So cross multiply, delta triple prime is equivalent to P1 times L over A1 times E sine theta. Okay? With that, we can now equate our two deformations. So delta 1 here, so delta 1 is equivalent to delta triple prime. So delta 1 is equivalent to delta triple prime. So what is delta 1? Delta 1 is, we have here delta 1, we have P2L over, do we have the same area? No, no, no. So we have area 2 times E is equivalent to what is delta triple prime? We have P1 L1 over area 1 E sine theta. Okay? So we have two unknowns here, but take note, we still have another equation here. So let's say this is my second equation. So from first equation, so from 1, I can say that P2 is equivalent to P, transpose this to the other side of the equation, likewise with this, is equivalent to P minus 2P1 sine theta. And substitute P2 here to there. Then we can now solve for the value of P1, given that we have a value for P. So substituting, we have, so substitute P2 in 2, we have P minus 2P1 sine theta divided by we have A2 times E is equivalent to P1 L over area 1 times E sine theta. And this will now be my working equation. Take note, you should have the value of P and you should have the above value of your theta. Then from there, you have your A2 as well and A1. You can now solve for the value of P1. If you have your P1, substitute it here, then you can solve for the value of P2. Then you now have your values for each of these three bars. Okay, so we have here problem number 3. A hollow steel cylinder surrounds a solid copper cylinder and the assembly is subjected to an actual load of 200 kilonewton as shown. So the cross-sectional area of the steel is 20 centimeters squared, while the cross-sectional area of the copper is 60 centimeters squared. So both cylinders are the same length before the load is applied. So you have here a 2 kilonewton load applied. So they have the same length before it was applied. So determine the temperature rise of the entire system required to place all of the load on the copper cylinder. So ano daw yung temperature change natin so that it is the copper who will be carrying the 200 kilonewton load. So the cover plate at the top of the assembly is rigid. So ibig sabihin hindi siya magde-deform. For copper, E is equivalent to 100 GPa. And this is lambda, or the coefficient of thermal expansion. It should not be 1.7. It is 17 times 10 raised to negative 6 per degree Celsius, while the steel, the modulus of elasticity is 200 GPa, and the lambda is 12 times 10 raised to um, negative 6 per degrees Celsius. Okay? So by this data, the coefficient of thermal expansion for the copper is greater than the coefficient of thermal expansion for the steel. Therefore, if we are to remove the steel here, or this material, or the cover, if we are to remove that, if we will be having a increase in temperature, we can say that copper will expand more compared to the steel, because from the coefficient of thermal expansion, the coefficient of copper is greater than the coefficient of the steel. So mas mataas yung kanyang magiging expansion. So here, what we're going to do is to use the compatibility equation. So how are we going to derive our compatibility equation? So first, we will be having a deflection due to thermal expansion. Okay? So for the copper first, we will be having the deflection of the copper due to thermal expansion, and our working equation would be alpha times delta T, or the temperature change, times the length. Okay? So, nag-expand siya pataas, so that is positive. So, that is alpha delta T times L. So, that is the expansion, thermal deformation. Now, if we're going to apply a load here, which is 200 kilonewton, magkakaroon ng compression. So, magkakaroon tayo ng another deformation. And that would be delta Cu. Okay? Is equivalent to, we are going to equate this equation with the thermal expansion of the steel. Kasi according to the problem, yung copper until is such a way na yung copper yung magbubuhat ng 200 kilonewton. So we can say na mag-level yung copper and yung ating steel. So therefore, the thermal expansion of the copper minus the deformation due to the loading is equivalent to the thermal expansion of the steel. Okay? So this is steel, this is copper times delta T, and that would be the length. Okay? So this now will be our working equation. Okay? So what is the coefficient of thermal expansion of the copper? The copper is 17. So we have here 17 times 10 raised to negative 6 per degree Celsius, times what is the length? The length here is 50 centimeters, and to make it in meters, divided by 100. So that is 0.5 meter. Minus what is delta Cu? Take note that the equation of delta is equivalent to PL over AE. Okay? Substitute this. We have P is 2,000 newtons. So that is 200,000 newtons times the length of 0.5. So we have 0.5 divided by our area. What is the area? The area is 60 for the copper. Okay, take note it is the copper who will be carrying it. So that is a centimeter squared. So to make it in meters, that would be 60 times 10 raised to negative 4, that is in meters, times the modulus of elasticity. And the modulus of elasticity for copper is 100 gigapascals. So that is 100 times 10 raised to 9 Newton per meter squared. Okay? Is equivalent to the coefficient of thermal expansion for the steel is 12. So we have there 12 times 10 raised to negative 6 per degree Celsius times delta T. We forgot here the delta T. Times delta T, and we also have here delta T times the length of 0.5. Take note, delta T here is and delta T here are the same because we need we need to have a same temperature in such a way na yung yung expansion ng ating steel is magiging exact sa magiging kapantay ng expansion at deformation ng ating copper. So they are one and the same. So input that in your calculator. Okay. And the final answer is 66.67 degrees Celsius. So delta T is equivalent to 66.67 degrees Celsius. So you need to increase your temperature to 66.67 degrees Celsius so that the copper, the cylindrical copper, will be carrying the 200 kilonewton load. And our steel will just be before the 200 kilo, the height of the copper. Next, we have here problem number 4. Consider the bolted joint shown. The force P is 30 kilonewton and the diameter of the bolt is 10 mm. Okay, so this is a problem of double shear in a bolt. Okay, so because we have a shear here and we also have a shear here. Okay, so therefore, the equation that we're going to use is 1/2 of the shear. Okay, so shear stress is equivalent to, we have P over A, but take note it is 1/2, so we will place 2 at the denominator. So we simply have 30. What is our force P? That is 30,000 newtons divided by what is the area. So the area here, you have the 10 mm diameter. So since we're using the diameter, it would be pi over 4 times the diameter of 10 squared. Okay, times 2. So shear is equivalent to 30 divided by shift pi over 4 times 10 squared times 2. It is equivalent to 190.99 Newton. Take note, this is in mm squared because the unit of 10 is mm. Newton per mm squared. Okay, and Newton per mm squared is equivalent to megapascals. Therefore, it is equivalent to 190.99 megapascals. And that is the shear stress. Okay, so we have here problem number 5. Low carbon structural steel has a shearing ultimate strength of approximately 300 megapascals. And determine the force P necessary to punch a 2.5 cm diameter hole through a plate of this steel, 1 cm thick. If the modulus of elasticity in the shear for this material is 82 gigapascals, find the shear strain at the edge of this hole when the shear stress is 143 megapascals. Now imagine you have here your steel plate. What I'm going to do is to punch a 2.5 cm diameter on this plate. So if I am to apply a load here, what is the load in order to punch a 2.5 centimeter diameter through this one thick plate? So since we are dealing with shear, the area that would be involved here, okay, would be the circumference times the thickness. Okay, I repeat, the area that would be involved here would be the area, would be the circumference times the thickness. So that would be the area. So for our working equation, we know that tau is equivalent to shear divided by the area. Okay? A divided by shear over A. Or it is just the same as P divided by A. But on this case, our unknown here is P. So, P therefore is equivalent to shear times the area. Okay? So, according to the problem, our shear is approximately 300 megapascals. So, 300,000 Newton per meter squared. Okay? Times the area. What would be the area? So, for the area of a circumference is equivalent to 2 pi r. But we have here a radius, therefore, circumference is also equivalent to pi d. Okay? So, the circumference is, uh, we have pi times the diameter in meters. So, 2.5 divided by 100, that is equivalent to 0.025 pi d times the thickness of 0.01, and that is our area. So P therefore is equivalent to 300 times 10 raised to 3 times pi times 0.025 times 0.01, and that is equivalent to 235. It should be in this should be in newtons. Wait, this is megapascal, so this is times 10 raised to 3 pa, times 10 raised to 3, so this should be times 10 raised to 6. So it is 235,619.45 newtons, or it is equivalent to 235.62 kilo newtons. That is the force required in order to punch a 2.5 centimeter diameter within the plate. Okay, the next unknown is to determine the shear strain, okay, of at the edge of this hole when the shear stress is 143 megapascals. So for the strain, we have our equation. Strain is equivalent to the shear divided by the modulus of elasticity of the steel, or it is the modulus of elasticity in shear rather. So our shear here is 143 megapascals. So 143 megapascals divided by the shear in the modulus of elasticity in shear, and that is equivalent to 82 gigapascals. So this is 82 times 10 raised to 3 megapascals. So megapascals will simply cancel out. So 143 divided by 82,000, and that is equivalent to 0.00174 rad, and that is the strain at 143 megapascals. Okay, so we have here problem number 6. A building that is 60-meter tall has essentially the rectangular configuration as shown. Horizontal wind loads will act on the building, exerting pressure on the vertical face O that may be approximated as uniform within each of the 3 layers. Okay, so from the empirical expression for wind pressure at the midpoint of each of the 3 layers, we have the pressure 781 Newton per meter squared. The lower layer, 1,264 Newton per meter squared at the middle layer, and 1,530 Newton meter squared per meter squared at the top layer. So determine the resisting shear that the foundation must develop to withstand this wind load. Okay, so take note for this problem, we will be combining all of these all of these forces in order for us to determine the total horizontal shear force that the foundation should resist. Okay, so first things first, we have here 781 kilonewton per meter squared. So we have here per meter squared. We need to convert that into force. Okay, so we have P1, P2, P3. So P1 is equivalent to, this is in pressure. So 781 kilonewton per meter squared. 781 kilonewton per meter squared times what would be the area. The area that is involved here is the area where our pressure would be uh, um, facing to, or kung saan siya tatama. That would be 20 by 50. So 20 meters by 50 meters. So meter squared will simply cancel out. So P1 is equivalent to 781 times 20 times 50. And that is equivalent to 781 kilo newtons. Okay? Next would be P2. So P2 is equivalent to 1,264 kilonewton per meter squared times the area, which is 20 meters by 50 meters. Meter squared will cancel. P2 therefore is equivalent to 1,264 kilonewtons. Okay. Next would be P3 is equivalent to 1,530. 1,530 kilonewton per square meters times what would be the area. We have 20 meters times 50 meters. Meter squared will cancel out. Therefore, this is equivalent to 1,530 kilo newtons. Okay? So, that's it. Using the equation of equilibrium, summation of forces horizontal is equivalent to 0. All forces that are towards right should be positive. So we have 781 plus 1,264 plus 1,530. 1,530 minus the horizontal force. FH is equivalent to 0. Therefore, FH is equivalent to 781 plus 1,264 plus 1,530 is equivalent to 3,575 kilo Newton. Now, what would be the shear that should be withstanded, or that should be withstand? Ano ba? Yeah. Anyways, what should be the shear force that needs to be resisted by the foundation? Okay. So shear stress is equivalent to shear force divided by the area. The shear force that is involved here is the 3,575 kilo Newton divided by the area. What is the area involved here? Take note, we are speaking of the foundation here. So the area involved would be the width times the length. So the width of 30 times the length of 50. So the area is 30 by 50 meters. Okay? So we have here 3,575 divided by 30 times 50 times 10 raised to 3, because that is in kilonewton. So this is 2,383.33, and this is in Newton per meter squared. Okay? Kasi kinonvert natin yung kilonewton. And if we're going to convert it back, pwede rin naman. We just remove the times 10 raised to 3, and that is 2.38 kilonewton per meter squared. So kilonewton per meter squared, that is kilopascals. That is also equivalent to 2.38 kilopascals. So that is uh, the shear stress that needs to be resisted. Okay. Okay, so we have here problem number 7. Two 1.5 mm thick strips of titanium alloy, 45 mm wide, are joined by a 45-degree laser weld as shown. Okay, so you have here two titanium alloy. It will be connected by a weld 45 degrees. So a 100 kilowatt carbon dioxide laser system is employed to form the joint. So this is the joint. So if the allowable shearing stress in the alloy, so the allowable shearing stress in the alloy is 440 megapascals, and the joint is assumed to be 100% efficient, so there is no reduction factor. Determine the allowable force P that can be applied, okay, for this system. So the first thing that we need to do is to draw our free body diagram. So this is my alloy. Okay, what I'm going to consider would be the right segment of my weld, but you can also consider the left segment of your weld. So what are the forces involved? So we have here the force P, and of course we have here the shear stress. We have here the shear stress, and we also have the normal stress. Okay, so tau. And the angle involved here is 45-degree angle. So next would be the cross-sectional area. According to the problem, it is 45 mm wide, and it has a thickness of 1.5 mm. So 45 by 1.5 mm. Okay, so using the equation of equilibrium, I can solve for the value of P. So summation of forces with tangential, because take note, we are given here the shear stress, and shear stress is the force being applied, or the force acting with the tangential to the cross-sectional area here. So therefore, the forces, or the stress that would be involved will only be the shear stress and the force P. We are not going to include our sigma here because sigma is a normal stress. We are only given the shearing stress, and shearing stress will not involve the normal stress. So the summation of forces tangential is equivalent to the shear, is equivalent to 0 first. All forces that are pointing towards this direction, let's say that is positive. So what are those? So we have here the shear stress. Then for the force P, of course, this is, since this is 45 degrees, the angle also here would be a 45-degree angle. So that would be minus P, and that is a that is adjacent. Okay, so that is cosine 45 is equivalent to 0. Okay, so but shear here is not a force, it is a stress. So shear is equivalent to P, let's say that is P1 over over an area. Okay, but take note here, our area here is inclined. So from our previous example, we derived the area, and that would be area is equivalent to, we have the base times the thickness over cosine theta. This equation here, we derived it from our previous example, from module 1 number 4. Okay, so P1 therefore is equivalent to the shear stress times the base times the thickness divided by cosine theta, and that is P1. So substituting this value here, we will be having the shear stress. What is the shear stress? Our shear stress is 440 Newton per mm squared. Take note that Newton per mm squared is also equivalent to megapascals. So Newton per mm squared times the thickness at the base of 45 mm. So 45 mm times the thickness of 1.5 mm divided by cosine 45 degrees. Our angle is 45 degrees minus P cosine 45 degrees is equivalent to 0. P therefore is equivalent to 440 times 45 times 1.5 divided by cosine 45 minus alpha x cosine 45 is equivalent to 0. Therefore, P is equivalent to 59,400 newtons, or P is equivalent to 59.4 kilo newtons. So that is the load, allowed load that can be applied on our alloy.